So welcome to another video. So in this video, we're actually going to talk about how do we distinguish enantiomers from diastereomers as well as Miso compounds um, in the Fischer projection, right? So uh, uh, it's pretty difficult, but we're going to make it pretty much easy. Now, I want to lay the foundations to make your life easier with respect to how would we differentiate with respect to all these compounds. So in the Fischer projection, which is what this video is really about, so I'm going to give a brief example of a Fischer projection. So this is an example of a Fischer projection. So this is an example of a Fischer projection. And the idea is, can you recognize, and I'm missing my hydrogen here, so that's not good. But the idea is, do you think this is an optically active compound? So does it have any stereogenic centers? Does it have any chiral centers? And the answer is yes. This would be my chiral center, right? I have 4 different things bonded to my central carbon. All right. So pretty simple. Now, the idea is, do you think this is R or S, right? So is this R or S? What's the configuration of the chiral center, right? And this, you should pause the video and then come back for the answer. Now, because Fischer, we use Fischer projections to draw a 3-dimensional structure of the molecule in really on a 2-dimensional plane, right? The surface is flat. We could only do rotations of 180 degrees. Now, something weird happens with respect to the chiral centers. So let's talk about how would we go about generating the chiral center for this, right? From the central carbon, I'm going to go out and find the heaviest atom, right, in terms of molecular weight. So oxygen obviously wins out. So this would be the first priority. Now, which one wins out between these 2 carbons, right? If I go out, I get a carbon. If I go out here, I get a carbon. The next one from here is actually a hydrogen, while the next one from here is actually an oxygen. So this will get the second priority. This will get number 3, obviously, because hydrogen is lighter. Right? Essentially, after the first 2 hydrogens, we'll end up with oxygen, right? So eventually this will win out and this will be your number 4. Now remember, according to the rule, you might be saying to yourself, why did I go straight to oxygen? Because it's always the highest molecular weight with respect to the branches that we go first before. So we go from highest to lowest, right? So in this case, because we have 2, we would actually go to oxygen first before hydrogen, right? So look, in this case, we're following the numbers. It's 1, right? So this is 1, 2, 3. So it'd be going around this way, right? So you would say to yourself, this is actually S, right? But please write this down. Please remember this. Because it is Fischer projection, the configuration of this chiral center is actually R. So R is the correct answer. So you got to remember that in Fischer projections, whatever configuration you get, you must flip. Right? So we kind of lay down the basic ground rules about how to determine the chiral center of these, and let's go to what we really came here for. Now, let's look at these 2 compounds. And my question is, are these enantiomers, diastereomers, or are they Miso compounds? Now, to eliminate Miso compound, the first thing you want to do is actually draw a plane of symmetry through the molecule. And if everything is the same on both sides through a plane of symmetry, so if I draw a plane of symmetry through the molecule and I get the same 2 things on the same side, then that means those are Miso compounds, right? In this case, obviously, that is not the case, right? So these cannot be Miso compounds. So the idea is, are these actually enantiomers, diastereomers, right? Because we've eliminated a Miso compound. Now, do you see any stereogenic centers in the molecule? And I see 1 here, has carbon that has 4 different things bonded to it, and here, right? So I have 2 stereogenic centers within the molecules. All right. Now, if you do the configuration, right? So because we have two stereogenic centers, if you do the configuration, let's do it real quick, right? We've kind of practiced here, but let's do it real quick. We essentially have from the carbon or chlorine will get our number one priority. All right, so our chlorine will get our number one priority. What would be number two? Right? If we go out here, we get a carbon. If we go out here, we get a carbon. But remember, bromine is here, right? So because we have a tie, if we go out one more here, we'll get a hydrogen. If we go out one more here, it will actually be the bromine. So this would be 1, this would be 2, and obviously the CH3 would be 3. All right, so essentially I'm going 1, 2, 3. So this is, right? So I'm going 1, 2, 3. So this is S. But remember, because we're Fischer projections, we actually are. Right? Now, if you do the same thing here, again, from this carbon, you go out, bromine gets number 1. What gets number 2? This carbon, right? Because remember, I go out one carbon here, I go out 1 here, I get a carbon, I go out 1 here, I also get a carbon, but eventually chlorine beats out the hydrogens, right? So this gets 2, this gets 3, right? So I'm essentially going R, but because of Fischer projections, we take the opposite. So this is S. Now, you should practice this by yourself, right? So tell me, what would the configurations be for this stereogenic center and this stereogenic center, right? And so if you do the configurations real quick, you would see that this is actually S and this is actually R, right? So we say that because we have alternating chiral centers, right? This is S right here, but this is R right here. This is R right here, but this is S right here. We say these are actually enantiomers, right? Let's do another one. How would we differentiate? Are these enantiomers, diastereomers, or Miso compounds? The first thing I like to do is identify my chiral centers, right? I have 4 different things bonded to this carbon as well as this carbon, right? And it's the same on this side. So I have 2 stereogenic centers. Now the idea is, are these enantiomers or diastereomers, right? Now, again, you could quickly do the configuration of the chiral centers, right? So oxygen in this case will get 1 from this carbon, right? From this carbon going out, right? Oxygen is the highest priority. The next one is, would it be this one or this one, right? If I go out, I get a carbon. If I go out 1 here, I get a carbon. Now, what's interesting is that if I go out here, I get an oxygen, but if I go out here, I get an oxygen as well. Now, this one would actually went out, right? So this would be number 2, and this would be 3. And the reason why is that because we have a double bond, we essentially count it as 2 oxygens. So essentially, I'm going this way, right? 1, 2, 3. So I'm going this way. So this is actually S, but because, again, we're in Fischer projections, this is R, right? Let's do this chiral center, right? If I go out 1, obviously oxygen is the highest, right? Because I go out here, I get a carbon. I go out here, I get a hydrogen. If I go out here, I get a carbon. So this would be 1. Now, what would be 2, right? Is it this one or is it this carbon, right? If I go out here, I get a carbon. If I go out here, I get a carbon. Now, if I go one more out, I get an oxygen. While if I go 1 more out, I actually get a hydrogen. So in this case, this would be 2. This would be 3. So this is going R, right? This is going R, but essentially because we're in Fischer projections, like we said before, this would be S. Now, do this one for yourself. And what you will actually find is that this would be S and this would be R. And again, like we said before, these, right? Look at carbon 1. Essentially, just if we're labeling this as carbon 1 and we're labeling this as carbon 1, you could see that 1 is S, 1 is R. And the opposite is true for the other carbon. So these are actually enantiomers. Now, if you haven't seen the pattern yet, please get this now. Essentially, if I have 2 R groups, and let's say I have a chlorine here and I have a hydrogen here, and let's say I draw another structure where this is probably R double prime, this is R prime, and now the chlorine is to the other side, and the hydrogen is to the other side. Typically, these are going to be off the opposite configuration, and maybe I should have R prime here, and this is R double prime. But you get the idea, right? So if you haven't seen, it's a weird pattern, but you should see this by now. Now let's go to another one. Wow, my screen just forgive me for that. Let me find my screen. Okay, so let's do this one. Pause the video and actually try to get it correct. Are these enantiomers, diastereomers, or Miso compounds? The first thing, like I said before, I always try to identify if I have any chiral centers. And in fact, this is a chiral center, right? I have 4 different things bonded to this carbon, and this is a chiral center. So we've identified that we actually have 2 chiral centers in our molecules. Now, do the configuration, right? Would this be R or would this be S, right? What would this be? Now, if we do this real quick, if we go out from this carbon, this would be 1. So that will get the number 1 priority. Essentially, I go out if I go out 1 here, I get a carbon. If I go out 1 here, I get a carbon. The next step out would be to the bromine. So essentially, this would win out. So this would actually get number 2. And this would get number 3. So this will get number 3. So essentially, we're going S. But remember that since it's Fischer projection, we're representing a 3D molecule on a 2-dimensional space. It's the opposite, right? And it's kind of really hard to, you just have to take that word. Unless you really take a model kit, you'll actually never really get to appreciate the stereochemistry. Now, what would this be, right? If I go out 1, right, from this carbon, right, bromine, right, will beat out both these carbons, so this will get number 1 priority. Now, essentially, I go out 1 here, I get a carbon. I go out 1 here, I get a carbon, right? So that would be a tie. So I then have to go to the next heaviest atom, right? Obviously, I don't have any choice here because the other three atoms are hydrogens, right? But the first atom that I would go to from here would be the chlorine. So this would get actually number 2, and this would be 3. So essentially, I'm going S, but remember, because we're in Fischer projections, we take the opposite. So this is actually R. Now, do the configurations for this real quick, based on the practice that we've had thus far. And as you could see from here, we haven't changed any of the atoms' positions. So this is actually still R. However, when you do this on your own, this is actually S. And so these are actually diastereomers. Why? Remember, the definition of a diastereomer says that a compound must have at least 2 chiral centers with 1 staying the same. So essentially, these, right, this carbon stays the same in both. It's both R. However, the top carbon or the top chiral center actually changes from S to R. So these are actually diastereomers. Hopefully you see the difference between a diastereomer and an enantiomer. Now, let's look at this one. Pause the video and tell me which one of the answers are correct. Now, we could actually go on and use our same strategy that we've used thus far to determine or enantiomers or diastereomers or Miso compounds. Now, you got to remember, Miso compounds still have chiral centers. They're not optically active, right? Now, if any time you suspect a Miso compound, like I did in the previous, well, not the previous example, but the first example, draw a line through the center of the molecule. Anytime, if you ever feel you need to suspect this may be a Miso compound. Draw a plane of symmetry through the middle of the molecule. Now, if you look at this, when I draw a plane of symmetry, I actually get the same two things on the same side. This is the same. They're the exact same thing on both sides, and these are actually Miso compounds, right? Look at this side and look at this side. They're the exact same things. Now, they're still chiral centers, right? And you could do the configuration, obviously, right? We still have chiral centers, but we say that they're equal and opposite, so it essentially cancel out. So these molecules actually have no optical activity. Now, I actually want to talk about one last question. And let's go back to this. And I want you to pause the video when I ask the question. And if you could actually answer it, it tells me that you've actually, you should tell yourself that, oh my goodness, actually I understand organic chemistry. Now, I'm going to ask you, of these two compounds, are there any more stereoisomers that I can actually get from these two compounds? So pause the video and answer that question yourself. Do you think I could get any more stereoisomers of these two compounds? The answer is actually yes, right? Remember the number of stereoisomers. Remember the number of stereoisomers possible is equal to 2 to the n, right? Where n is actually a number of chiral centers, right? So if you said yes, you are correct, right? So essentially, because we have two chiral centers, this would be 2 to the second power, which is actually be 4. So that means that we actually could get a total of 4 stereoisomers from this compound, or from this compound, right? So this is actually one of the stereoisomers of this compound, right? And the opposite is true. Now, let's do something here. Let's label this A, and let's label this B. Now, what would be a possible stereoisomer, right? Could you draw a stereoisomer of any one of these to give me the total of 4? Well, the answer is true. What I could do is actually hold one of these chiral centers the same and actually change the atom from one side to the next. And we kind of talked about this right here, right? We said that if you flip the atoms with obviously different alternating groups, then you could get the chiral centers to be changed, right? So essentially, if I let this stay S, so I'm going to write my CH3 on that first chiral center, I'm going to keep it the exact same. However, I'm going to flip the bromine. So the bromine now becomes on the left, the hydrogen comes on the right. And that is, let's say we're going to label this as C. All right. Now, do you think what would be the last stereoisomer of this compound? Right? I could actually hold this one constant, right? So now I could actually hold this one constant and flip the bromine, right? So essentially, right, so let me label my chiral centers. So this is S, right? This hasn't changed, but we flip the bromine, right? So this becomes S, right? And the last one, I'm actually going to let you guys do on your own. All right, so figure out the last one, put it in the comments, and if you figure out the last one, you should tell yourself you understand organic chemistry. Now, one of the things that I wanted to ask was, what is the relationship between B and C? Right? Do you understand the chemistry? What is the relationship between B and C? And in fact, these are actually diastereomers. right? Remember, diastereomers, what we're saying is that you have at least two chiral centers with one being the same, right? So this chiral center, you can see this is S and this is S, right? So that stays the same. However, we have one that alternates, right? This is S and this is R.